Let's begin. So we're going to start with the topic of rational exponents. Right away, rational means what? What does rational mean? Good, fractions. If you didn't know that, write it down again. Because we've talked about this with rational functions, right? Whenever you see the word rational, think the number can be written as a fraction. When you see the word rational, it means that that number, whatever it is, in this case the exponent, can be written as a fraction. Now, if you go online, right, and like say in a week or so, or tomorrow, or tonight, you want to maybe do a little bit more research on your own, or watch a video on YouTube, some authors call this fractional exponents. Same thing, rational, fractional. Okay, whether it's called fractional exponents or rational, it's the same thing. We're just recognizing that you can search for either of those if you want to. So we're going to define them, we're going to use them, and then we're going to solve equations containing them. So let's start with this first slide. So this is some prior knowledge, right? Recall, when I say the word recall, it means recall from prior knowledge. And we've done this already. From prior knowledge, we said that, you know what? We can find a root of an equation because of the fact that x to the n equals some number. So if I have like, I don't know, in this case, x squared equals 16, what's x? 4. Take the square root. So we talked about this earlier in the year. We talked about how, you know what? If I want to get x by itself, how do I get rid of an n as a power? I can raise it to the 1 over n power. Well, let's show this so you guys can see what I'm saying here. So if I have x to the n equals b, and I want to solve for x, I can raise both sides to the 1 over n power. What happens when you raise x to the n to the 1 over n? When you raise a power to a power, what do you do with those powers? In this case, they will cancel, but what's the rule? When you raise a power to a power, you multiply. N times 1 over n, cancel. So that's just going to become x in this case. And then the right-hand side is b to the 1 over n. Again, if I want to get rid of a power, I can raise it to its reciprocal power. Raising it to a reciprocal power, when I multiply reciprocals, I always get 1. So this solves for x. And you're like, okay, what does this b to the 1 over n thing now? How does this work? Well, take a look. This is what we learned earlier in the year, that x was equal to the nth root. Well, that's what this is. B to the 1 over n is really the nth root of b. So if I have like, I don't know, the square root of 16, it's the same thing as 16 to the 1/2. If I have the cube root of 8, it's the same as 8 to the 1/3. So anytime I'm raising a power, a number, to a power that is a fraction, I have to consider what each part of the fraction means. So let's look at this breakdown here. This is an extension of what we're doing here. So if I look at a fraction, or a number b raised to the fraction a over n, this is the exponent. A over n is the exponent. I could think of this as b to the 1 over n to the n. How come these are the same? Again, as Alex told us, I can raise a power to a power by multiplying. 1 over n times a is just a over n. So this is the same thing so far. Now, based on our definition from here, b to the 1 over n is the same thing as the nth root of b. So I can take this part right here and replace it with the nth root of b, so to the a power, and get this result. So what this tells us, this is a little, I don't want to say shortcut, but this is the way to remember it, is that the numerator of the exponent becomes the power. The denominator of the exponent becomes the index of the root. Numbers in a minute, and everything. Oh yeah, I get that. But I want you guys to start understanding theory more than just numbers. And that's what differentiates an honors and a non-honors class. In an honors class, you're going to be given a number with examples and follow a rule over and over and over and over until you just get it. Whereas I'm teaching you the theory behind why this actually makes sense. Again, the numerator of the fractional exponent becomes the power. Whether it's here or here, these are the same things. The denominator of the fractional exponent becomes the index of the root, the nth root of whatever we're doing. So anytime I see a fractional exponent, I know that it's going to be something with a radical and something with a power. It always translates to that. So let's look at a quick example with a number such as 10 to the 2/3. Or let's start with 10 to the 10 to the 2/3 is fine. And if I want to rewrite this, I would say this is really the third root of 10. That's the denominator, becomes the index of the root to the second power. Again, the denominator becomes the index, the numerator becomes the power. Depending upon each of you individually, you may decide to memorize this. Whereas some of you may think, oh, you know what, I understand the theory behind it, I know it. In the end of the day, you will memorize it inherently. Whether you do or don't really understand the theory, you have to memorize this. Even if you do understand the theory, it will become second nature to you, like a right-handed rule, if you will. Okay?
I have a question. Probably you might be wrong, but could you also do like 10 squared divided by 10 cubed, or not?
No. That would be 10 to the negative 1. Think about it.
Oh, yeah.
If you have 10 squared over 10 cubed, you have to subtract the exponents, right? You'd get 10 to the negative 1 there. I see what you're saying there. Good question. Yeah.
So you could also put the 2 under the radical.
Yep. So I'll write or, and it would be cube root of 10 squared. Either way is fine.
Would that just be like your answer?
Yeah, this is not a problem we can simplify any further because there is no cube root of 10. That's an integer number, right? I can't do it. Even if I do 10 squared, is there a cube root of 100? No. So I can't do it. So I can't go any further. But, Julia, at times, if this were like an 8, cube root of 8 is just 2. 2 squared is 4. So if this were an 8, you could also just do 8 squared is 64. The cube root of 64 is also 4. So whether you do it this way and then square it, or square it, then take the root, it's the same thing. Some problems are easier than others to do one way though. So if I had like the cube root of 125, that's just 5, right? It makes sense to do that first to simplify. Because if I did the cube root of 125, but 125 was raised to the 5th power, now I got to do 125 to the 5th power, and the cube root of that. It's a mess. So we'll see when it makes more sense to use one or the other. Okay? Very good question. I saw another hand. Good? Okay. So let's look at our examples for this. So this just says simplify. So we're going to practice 4 times doing this. I'll do the first one with you. This becomes, again, the denominator is the index, so this is a square root. I don't have to put a 2 there. I'm going to do it just to emphasize it. I don't need the 2 there, though. Square root is inherent. And this is 4 to the 5th. Now, I could write it like that, or I could write it like this. Raise your hand and answer which way is the right way to do it for this problem. They're both correct mathematically, but which is the better way? Yes, how come?
Because then if you don't have parentheses, you have to probably simplify.
Yeah. Who wants to do 4 to the 5th, right? Figure out what 4 to the 5th is. 4 to the 3rd is 64. Do I want to multiply by 4 again twice? No, I don't want to do that. And this is going to be part of the test where you don't have a calculator. So instead, what do? You do it this way, because the square root of 4 is just 2. 2 to the 5th is easy. 32. Answer. We're done. Okay, again, this becomes really a 2, and since it's to the 5th, that answer gives you 32. Try B on your own. Use the same technique identically. Numerator becomes the power, denominator becomes the index of the root every single time. You can definitely do the second one on your own. The 3rd and 4th are a little tricky, but they're not any more difficult than this one is. Should be done at this point. Number 2, with part B. Okay, it's literally 3 lines. Rewrite it. Cube root of negative 8 is negative 2. And then negative 2 squared is 4. But you're taking the same approach. Mark. It is in this case. Now, yes, for all real numbers, it does not matter. Hypothetically, for imaginary numbers, it's different. But we're not going to see that in this case, so it doesn't matter. Yeah, because you squared negative 8, got 64. Cube root of 64 is 4. Yep, that works. But I think, Mauro, that this is the approach that you're going to want to take more often than not. Okay, because of the fact that, yeah, 8 squared is easy to do, right? But let's look at this next one, or these ones coming in next, right? Because 9 to 3.5, let's start with that right away. Am I going to write 3.5 as my exponent? What do I write instead? What's 3.5 really? 7 over 2. So let's take part C and start by just rewriting this as 9 to the 7/2 power. And now, Maura, do you see why it makes sense to do it this way? Okay, so it's going to be then, this becomes the square root of 9 to the 7th power. Do not do 9 to the 7th. Right? 9 to the 7th is a mess, and then you got a square root. So the square root of 9 is just 3. Unfortunately, 3 to the 7th is not very nice either. Everybody got it? Anyone know that one? All right, I don't even know it off the top of my head. 3 cubed is 27, 3 to the 4th is 81, 3 to the 5th is 243, 3 to the 6th is going to be 7 and change, 3 to the 7th is going to be like 2,000 something?
2,187.
Yeah. 2,187. Okay? Now, again, as much as it seems like that's difficult, it's way more difficult to do 9 to the 7th, right? Although that was a bit tedious and long, to do 3 to the 7th power, I didn't show the step here, right? This is really 3 to the 7th. 9 to the 7th is far more difficult than worrying about 3 to the 7th. Last one. I'm going to just write it so you can see it. So again, remember, you're referring to these videos at home now. Okay, I don't have videos under Mr. Howell's videos. These are only videos from class right now. So if you missed something, I'm trying to make sure everything's getting written down. So tonight, if you want to go back and scroll through to see what you missed, you can still see it. Christian, help us out with part D.
Right.
What do you suggest we do to start part D?
You changed it to, in the index of the root would be 225 negative third.
So the square root of 25 to the negative third. I'll do that. That sounds good. Next.
Then you simplify the square root of 25 to become 5 to the negative third.
Agreed.
And then that would be 1 over 5 to the third power.
Which is?
1 over 125.
Well done. 1 over 125. Okay, 1 over 125. And I should not draw my fractions slanted. I don't know why I'm doing that. I never do that. You really should never draw your fractions like this. I think in your exponents it's convenient, but when you're writing fractions normally, try to write them like this. It's much more clear when it comes to equations. Idea okay? Right? So the theory's there. If the theory didn't sit well with you right now, it's okay. Let it sit for a couple more days, maybe come back and revisit the theory. But the rule is very easy to follow as you practice this more and more and more. Yes?
So for the square root of 25 to the negative third power, if I instead of writing to the negative third power, if I put
1 over? Yeah, you could start 1 over earlier. So what Isabella's asking is, can I write this as 1 over the square root of 25 to the positive third in the beginning? Yeah, because then you got 5 to the third still on the bottom instead of the same answer. Whenever you have a negative exponent, you can address it initially or at the end. It doesn't matter. Either way is fine. I personally, I guess I don't have one way or the other that I do it. Either way is fine. Okay? All right. Now, let's take this concept and go a little bit further, right? Where we now have no numbers. And all I want you to do is write this in exponential form. So underline that phrase, exponential form. That means written only with exponents, no radicals involved. Your book tends to ask this question, so I want to make sure you understand the wording of it. Written in exponential form simply means without the square roots or the radicals. Okay? So what are we doing here? We're going backwards. We're going backwards. What is a square root really? What is a square root really? What power is a square root? 1/2. What power is a cube root? 4th root? 1/4, right? We see that? So this is really okay, that's really what it is. Get rid of your radicals in your mind if you have to, and start using fractional exponents. 1/3 power is a cube root. But now that everything is raised to the 1/2 power, when I raise a power to a power, what do I do again? Power to a power. So this becomes, A is really to the 1. I'm going to put it in blue in case you don't see that. For those of you that are forgetting, A has a power. The power is 1. So A to the 1 to the 1/2 just becomes A to the 1/2. B to the 6 to the 1/2 becomes B to the 3rd. C to the 3rd to the 1/2 becomes C to the 3/2. And that's it for part A. Again, I'm distributing, I know the word is not mathematically correct to use here, but I'm distributing my power to every factor in the expression. These are all factors, right? Factors. They gotta be factors for this to work. Go ahead and try part B. Go ahead and try part B. So Isabella asked earlier about the negative part. Move it now or move it later? It's up to you to decide. Don't worry about the negative if you don't want it right now, but at the end, we'll move things around. Can I leave it like that? Anything else I can simplify? I can move my exponents, I get that piece, and we'll talk about when it's good to have positive and negative exponents. Like here I left a little positive. I could have moved the C up, make it negative if I wanted. But there's something else I should probably want to do still. You see it, Alex?
Is it the 27?
Yeah, what's 27 to the 4/3 really telling us to do?
8.99.
You just put in your calculator? Yeah, don't use your calculator for this. You're not going to be able to use it in test. You got 80.99. It should be 81. That's the error your calculator gives you because you rounded, right? It's 81 is the answer. But what is 27 to the 4/3 is my question.
You just do the same process that you did.
Yes. So what would that process be? Go ahead.
27, or this cube root of 27, and then we'll put it to the 4th.
Good. To the 4th power. And that's really just 3 to the 4th. Okay, that's really just 3 to the 4th. I'm going to kind of use my arrows in a weird way. And 3 to the 4th is 81. 81 b to the negative 1 over a to the 4/3. Now, let's talk about this point right here. I am not a stickler. You guys know about this. I'm happy that you understand stuff. Now, some teachers later in life might say, express your answer with all positive exponents. Just follow the directions. Which would mean, take b to the negative 1, move it down below as b to the positive 1, and all your answers have all positive exponents. I don't know why teachers do it. It honestly doesn't matter anyway. It's more about like teachers just want to be very particular because they have an answer key and they don't want their answer key to look different. It does not matter whether you write it like this or move the a up and make this a to the negative 4/3. I don't care. It doesn't make a difference. When will it matter though on what kind of questions will it matter? Multiple choice. So although I don't care, we have to still understand how to manipulate properly. So leave it like this if you want, or if you want to, continue going. We could say this is really 81 over b a to the 4/3. That's with all positive exponents. Or maybe the multiple choice answer is 81 b to the negative 1 a to the negative 4/3. These three are all the same. It does not matter which one you choose to leave it as, except when the directions tell you one way or it's multiple choice. If the negative exponent part, it doesn't matter. It really doesn't matter. And move this down, gives you this. Or take this guy, move it up, make it negative, gives you this. Same answer for all of them. Questions on this example 2, either A or B? Yeah?
How did you move from 27 to the 4 over 3rd power to 3/7?
Yeah, so here I realize that this is 27 to the 4th, right? but it's really 27 to the fourth with a cube root. So it's a cube root of 27 to the fourth. So I could have gone right from this to here if I wanted to. Just take the 4 and move it outside, which I'm going to have to do. Or, after I recognize that this was a 1/3, to the fourth power makes this 4/3. 4 times 1/3 is 4/3. The 3 becomes the index. The 4 becomes the power from my earlier rule. Okay, so it's a bit redundant, right, by me changing it to this and then going back to this. So you could have kind of done it in the beginning, but it's not obvious always when you're doing these problems to do it that way. Okay? Yeah, whenever it's a number, simplify it if you can. Whenever it's a number. Variables, you can't really simplify as much. Okay. Let's go to example number 3. Simplify and give the answer in exponential form. Just more practice. Giving the answer in exponential form. So let's look at part A first. If it says exponential form, I don't want radicals. So the first part of part A is fine. Right? They're just variables. But then I've got the radical on the right side there. So let's start by copying the first part of part A. But then this is times whatever this is over here, which is b cubed a to the 7th to the 1/4 power. So again, I'm only taking care of the parts with radicals. The parts with rational exponents, we're going to utilize them in a minute anyway. A power to a power, by now we know we multiply those powers. The 1/2 stays, the 3/2 stays. This becomes b to the 3/4. This becomes a to the 7/4. Eduardo, when I'm multiplying with the same bases, what do I do to the powers?
If it's the same base, then you just multiply the numerators.
Careful. When I raise a power to a power, I multiply them. Power to a power, I multiply them. What's x squared times x cubed? What does that give you? X to the third. So what did you do to the powers?
Oh, you add them.
Very good. Go back to your rules of x, right? It makes it easier. So a to the 3/2 times a to the 7/4, I need a common denominator when I'm adding these fractions. Same thing here. I need a common denominator when adding. Okay, so if I continue down to make it look a little nicer, this becomes b, that's a b, sorry, to the 1/2 plus 3/4 power times a to the 3/2 plus 7/4 power. Again, 1/2 plus 3/4, I'm adding the powers. 3/2 plus 7/4, I'm adding. Common denominator is obviously 4 in both cases. Bless you. Common denominator is obviously 4. This becomes b to the 2/4 plus 3/4 times a to the 6/4 plus 7/4. Which gives me a final answer of b to the 5/4, a to the 13/4. Okay. Now, I could, and I'm going to show you this, but you don't have to. I could go one step further if it's multiple choice. Can somebody give me another way to write this final answer? It looks different, but it's the same. You got it?
Would it be, BA or BB?
Yep.
The radical for
So you could start with a 4 in here, very good. What would the exponents though be then?
B to the 5th and then A
Good. Or what else could I write this as? Give me one more. That's one option. Good. Very good. That's not an exponential form, but multiple choice it could. How about one more option in exponential form of what you see there?
We could just like switch A and B.
Yes, that doesn't change. Yeah, I like that idea though. Yeah.
B to the 5th times A to the 13th. The quantity of that times 1 to the power of 1/4.
Very good. I like your wording. Way to correct yourself. To the power of 1/4. Any of these three are the same on the right, okay? What's circled is absolutely correct, but if it's multiple choice, those next two could be one of your options. And just make sense of it in your head. Look at the word. These both have a 4 in the denominator, which is why Valentina said, you know what? It's like I'm raising these to the 1/4. Because if I were to multiply that 1/4, I'd get back to here. 5/4 and 13/4. So that's part A. Let's go to part B now. I'm going to write it down a little bit lower. Part B says the square root of x cubed that to the 1/3, that to the -3/4. Looks confusing because you have a radical and you have exponents. So what makes sense to do here? What does it make sense to do right off the bat here? I don't want to deal with radicals and exponents, so
We multiply everything. Don't make a common factor.
a common factor. You need things to be common, yes, but not in that sense.
Can you make the x cubed into like a fraction?
Yeah. Start by getting rid of your radical by thinking of this as x cubed to the 1/2. And then that's the 1/3, and that's the -3/4. So you want all exponents. You want to deal with radicals and exponents together, right?
Can you make it x to the 3/2?
Yes. And I'm going to, you see that already, do that. But I'm going to show the steps. So this is really x to the 3rd to the 1/2. And then that's to the 1/3. And that's the -3/4. So this right here, I'll show you, I'll circle it, is the same as this. Okay, circled in yellow, those are the exact same things. Again, the square root is a number to the 1/2. So the square root of x cubed is x cubed to the 1/2. And then that's still raised to the next powers. So Julia picked up on it already, obviously. And you know what? If the index is 2, and the power is 3, this is really just x to the 3/2. What's circled in yellow is really x to the 3/2. So I would agree with her that if you see that, it makes more sense to write it right away. And then the rest of it carries over. Now, once everything's in fractions and I raise a power to a power, what do I do to those powers? Which one? Which one or the other? Power to a power. Multiply always. Multiply when it's power to the power. So if I have like x squared to the 5th, it's x to the 10th. It's x squared, x squared, x squared, x squared, x squared, right? That's what the 5th is. So whenever you have a power to power, multiply. So start here, this power to this power, multiply these two, right? You get a number. That'll be your new power to this power, multiply those. So in the end, I'm going to multiply all 3 of these, right? So it doesn't matter if I multiply them all at once or separately. Let's see, what do we get? This is going to give us 3, 1, -3 is -9. This will give me, we can cancel, I guess, so yeah. So 6 and 4 is 24. -9 over 24 reduces to 3/8. Absolutely. Yep. Okay, so if you want to see this mathematically, this becomes x. So 3/2 times 1/3 gives me just 1/2. And then next line, this becomes x to the -3/8. Okay, again, all I did was simplify this right here to become this right here, what's boxed in. So if you're not sure what I'm doing, take a look at the colors to help you with association. What's in the green box here became what's in the green box here. 3/2 times 1/3, 3's cancel, 1/2 is left over. 1/2 to the 3/4 is 3/8, carrying down the negative sign. Fractions, fractions, fractions. Got to know your work with fractions. Got to know how to add, subtract, multiply, divide, fractions, LCDs, all this stuff, right? But also now taking all those fraction rules and putting them in with exponent rules at the same time. Let's do one more example for today. Example 4. Now we're going to look at equations. Same technique we just used, but with equations. Can somebody suggest what they think I should do for the first one here? For the first one, Alex, what do you think? Can't divide by... Oh, actually, no. Divide by 6 works to start. Yeah, absolutely. Agreed. Very good, Alex. Do you know the second step? We haven't done this yet, so it's definitely something new. But you could probably figure it out if you just work through it. What do I want to get by itself? What's the goal in this problem? So what do I got to get rid of? So what power can I raise 2/3 to get rid of it? Very good. 3/2. So write yourself a note. Step 1. Isolate the variable with the exponent. Step 1. Isolate the variable with the exponent. Step 2. Raise both sides to the reciprocal of that exponent. Step 2, raise both sides to the reciprocal of that exponent. So step 1 is isolate the variable with the exponent. Step 2 is raise both sides to the reciprocal of that exponent. So yes, Alex is right. Let's raise these both to 3/2. On both, if I do something to one side though, I got to do it to another for equations. So let's do this and this. Now, as Alex said, if you raise something to its reciprocal exponent, what do you just get? Only the base by itself. So this is just going to give you x on the left side. But what's 9 to the 3/2 power? What is it?
27.
Why?
Because then you find, so then 9 to
There you go. Step
3 times the root of 9 becomes 3, and then 3 to the cube becomes 27.
Very good. You take the square root of 9, because the 2 is the root, that'll give you the 3, and then cube it to get 27. So if you're confused, all you got to do is rewrite like we just did. The 2 becomes the index, the 3 becomes the power. The square root of 9 is 3, and 3 cubed is indeed 27. Okay, well done. Christian, well done. That helps, the beginning part. The next 3 are identical. There's no difference whatsoever. It's all about step 1. If you can get through step 1, step 2 and 3 are very easy. Step 1 is just isolate the variable with the exponent. So just like Alex divided by 6 earlier, let's get rid of that negative 3 for part B. Do part B on your own, please. Do part B on your own. Don't let the negative exponent throw you off. The reciprocal of negative 3/2 is negative 2/3. It's the same thing. You don't change the sign, you flip the fraction. Don't let the negative throw you off. I'll be one step behind you. You can check as you go along. So divide by 3 first. Raise both sides to the reciprocal power. And rewrite nicely. Check your work, please, when you're done. Check your work when you're done. Notice I waited till the very end of this problem to take care of the negative exponent. I didn't care about it originally. I took care of it at the end of the problem. Let me know if that's confusing, because C and D are a little tougher, not much, but a little bit tougher. So I will happily go over part A or B again if you want me to. Yeah?
Does it matter, like, when you take care of the negative exponent?
No. No. You want to do it early, you can. I personally like to do all my work first, and then at the end of the problem, if I have negative exponents that are not either in a choice, because it's multiple choice, then I deal with that. Because on a short answer on my test, if you leave your answer with a negative exponent, that's fine with me. You know? If it's a multiple choice, though, just take care of it at the end. Because why do the work at the beginning if it doesn't matter, right? See what I'm saying? Multiple choice would matter, obviously, though, but for short answer, it doesn't matter. So don't worry about it until the very end.
For C, would you add the 4? I mean the negative 3 to the
Yeah,
first
very good. So just like you solve any other equation, get rid of the 3 by adding it over.
And then would you distribute the...
No. Let's talk about this one now. So let's go into what do you think maybe you would do instead? So this becomes this. Let's start with this. So as Alex said, definitely add the 3 over. Let's take a look at C together. Add the 3 over for short. Add the 3 over for short. Yeah.
You have to add the 2 as well.
Can I? Is the 2 by itself? The 2 is not by itself. If it were, you would add it over, obviously, right? Well, how do I get rid of the next one? Raise it to the reciprocal. So you know what? T minus 2 is your quote-unquote variable right now. I know that's weird, because step 1 said isolate the variable, right? But can you isolate this variable, actually? You can't. There's no way to get t by itself until you get rid of the power. You've got to get rid of the power first, and then you can add the 2 over. You see what I'm saying? Write yourself a note that quote-unquote t minus 2 acts as your variable here. So let's raise both sides to the 5/2 power. And what that gives me on the next line is t minus 2 equals 4 to the 5/2. Take a look and make sure that makes sense why I did it that way. 2 is on the inside of the parentheses. I can't just arbitrarily take it out. It'd be like saying x plus 1 quantity squared and just take out the 1. Can't do that. It's inside the parentheses, which is all being squared. Can't do it. Okay, you cannot get rid of the negative 2 initially. Now you can. Now you could say t equals 4 to the 5/2 plus a 2. Right? Move the 2 over now. But what's 4 to the 5/2?
32.
Where do you get 32 from?
Right. Could you just say,
Tell us, go ahead.
so it's just 4, or the square root of 4 to the power, and that's just 5. I mean, that's just 2 to the 5th,
Which is?
32.
Very good.
Just add it.
If you want to, do you remember when we used dummy variables? I called them u substitution. Remember when we had like weird things? We said let x equal whatever's in the inside. You could let u equal t minus 2 in this problem. Whatever argument is in here, you could let that equal u. And when you solve this, you'll get u equals 32. Well, if t minus 2 was u, you add the 2 over, you get back to 34. So if you like to use u substitution again for this kind of a problem, where the argument, I call this argument, so it's the right math word for it, it's called the argument, where the argument is not just a variable, right? It's not a variable just alone, you can use u substitution. So let's use u substitution for part D. You don't need to. If you don't like to, just do it the regular way. But I'm going to do it. Okay, part D, I've got the following. 3n minus 1 as a quantity to the negative 2/3 equals 1/16. So I'm just going to start with that to write it down. Now, if I want to use u substitution, I let u equal whatever's on the inside. Which makes my equation now this. At the end, I'll solve for u, plug that back in here, and then solve for n. Again, I'll solve for u in this equation now, plug it back in for u, and then get n. If you don't like u substitution, don't do it. You don't need it here. It's not necessary. You can easily solve this by raising both sides to the negative 3/2 power. You get this by itself, add the 1, divide by 3. You can absolutely do this without u substitution. Okay, you know what I'll do is I'll do it both ways. We have enough time today. So on the left side, we'll use u substitution. And on the right side, I'll do it the other way. So let's do u substitution the whole way through. So now, this becomes negative 3/2. Negative 3/2. That gives me u equals 1/16 to the negative 3/2. What's the deal there? How do I evaluate this? Because this is a problem that a lot of students run into. How do I evaluate a fraction written to a negative exponent? What do you think?
What I did was I did u equals like the square root of 1/16 because that's just 1/4, and then I got 1/4 to the negative.
Yeah. So you can take this, make it your power on the outside, leave the negative exponent for a while, and then figure it out after. You like to work with the negative sometimes earlier. So if you want to, we know this. If you make this positive, what do you do to the fraction? To make this positive, what's your rule? I know your rules, guys. It's one of our big rules. There's rule number 6 or 7 in the rules of exponents. If you make this sign positive, the fraction has to live. So you can just make this 3/2 and put the 4 up top. It's the same thing. Exact same thing. Okay, I'm going to go with the way that Eduardo said. So this is really the square root of 1/16 all to the negative 3rd. The square root of 1/16, as Eduardo said, is indeed 1/4. Because the top is square root of 1, which is 1. The bottom is 16, which is 4. To the negative 3rd. Now, a number to the negative 3rd, now we're going to have to flip. We're going to have to figure it out, right? This is going to become 1 to the negative 3rd or 4 to the negative 3rd, which ends up flipping them both. So on the next line, I'm going to write this. I'll go this way because I'm running out of room. I'm going to write this as u equals 4 to the positive third, which gives me an answer of 64. Am I done?
No, you just put the
Back into the...
3 and multiple.
Yeah, go back to your let statement and plug 64 in for u. Go ahead, take 64 here, plug it in for u right there. You'll get an n value in this problem. You get an n value of 65 divided by 3.
Or could you just divide by 3 first? So that'd be easier. 64 divided by 3 first.
And then what?
And do the...
This
It's simpler if you just do...
this equals, remember, this goes back into place for this, right?
I'm not assuming if it was easier to divide. first.
Well, PEMDAS, you got to do the other way. You can't divide first there. Right? That's the route I would take. Again, if you don't like u substitution, do this without, guys. Okay, do it without. You don't need u substitution. So your homework's on the next slide. It looks like a lot of questions. The first like 5 or 6 are just rewriting from one form to the other. It should take you the first 5 or 6 like 10 seconds each. Later on, you definitely have equations like that to work on. And then I give you some review work for rational functions. Review work for rational functions. I definitely would look at that. Okay, some of you definitely need to review your rational functions still. I don't have your test grades yet, but when I do, I'll let you know as soon as I do. Okay? Have a good day, guys.